Okay, let's look at Proposition 63, which is a unified geometry transversal theorem. Specifically, we're going to prove part B, the Z property, the part that we get in, well, really it's in neutral geometry, because we already say the metric is unbounded. Okay, so let AB be a transversal to lines CD and EF so that X is, we have the order A, X, Y, B, so those points are in that order. X is between C and D, Y is between E and F, C is not on AB, E is not on AB or CD, E is on the same side of AB as CD, and and this is going to assume that X and Y are distinct here. Okay. Alright, now, boy, that's a mouthful to say all that. Okay, so let's take a look. Of course, that's going to be our hypothesis. Okay, along with the fact that the Z part says the metric is unbounded, and we have a pair of alternate interior angles that are congruent. Our conclusion is going to be then that we get the lines CD and EF parallel. So there's a mouthful when you say all that, but let's take a look at the picture. It's a lot easier to just draw it than it is to state all of it. So what we have is we have these two lines, CD and EF, and then we have a transversal, AB, that intersects them at points X and Y. And we've set this up so that X is the point here on line CD, and it's between C and D. We do this so that we can refer to all these angles. That's why we need to establish all these betweenness relationships here in the hypothesis. And then we have EF has Y between it, so that X and Y are these points of intersection. And then we put A up here and B down here. And so again, this is so that we can identify the correct angles here. And so what we're going to assume is that these angles right here and here, that is angle CXB, is going to be congruent to this angle, that's the one right here, and it's going to be congruent to this one right here, which is the angle AYF, or FYA. Okay? Now this is called the Z property sometimes. I've seen a couple books that use this notation. Sometimes they'll just this is not universal notation. But why is it called Z? Well, if you have the letter Z, it forms an angle here and here, and those are the ones that we're assuming to be congruent. And then what we're going to prove is that these two lines are parallel, and we'll mark them like that when they're parallel. Okay, and we want this to be true in not only in Euclidean geometry but hyperbolic geometry. We want to prove that. Okay, so there's your Z, and so you can see the Z right here with the angles, the pair of alternate interior angles congruent. So one direction of the Z property is what we're going to prove here, and that is that if those alternate interior angles formed by a transversal to two lines are congruent, then the two lines have to be parallel. Now let's see what this looks like in the hyperbolic situation. Here we go. By the way, the points that manipulate the drawing up here are the yellow points. Okay, and we can make this is done in a dynamic way. Okay, and it's drawn in such a way that all the things that we ask for are always there. For example, that C stays on the right, on the opposite side from D, and so forth. At least in the Euclidean one, I think the hyperbolic one is there, almost there too, down here. Now, in this case, what you're going to find out is that another part of the theorem says down below that when this happens, that actually all these angles I've got marked as red are congruent to each other, and all the ones that are marked as green are congruent to each other, and then the two lines are parallel. We're just going to prove in this part that the two lines are parallel. Now here's the same picture down here with the same labeling. Here's your line CD, here's your line EF, and here's your transversal here, and these are of course hyperbolic lines. Again, the yellow points will be the control points, and this was constructed in such a way that by using rotation commands and so forth, that this angle right here, this angle C to X to B, is the same size angle as the angles from F to Y to A. So these alternate interior angles here are constructed to be congruent. And what we notice is when we move this around, the two blue lines don't intersect. Remember, we don't want them. At one point they're concurrent, because then the transversal is not really transversal anymore. The purple and the two blue lines are the same. That's the degenerate case, which is not included in our hypothesis. And you can see that those lines stay parallel. My angle markers got off a little bit there at one point, but basically they stay parallel. And the same thing is true up here. They're parallel here. Okay, so there's your illustration. Basically, we can refer back to the illustration from here on, even though, technically we should be referring to the construction here, but it's all built into the illustration. Okay, now we're going to do this as a proof by contradiction, so we're going to assume that CD is not parallel to EF. So that means there must be an intersection point Z which is on both CD and EF. Now, I first claim that Z cannot be on the transversal. Okay, if Z were on, well, first of all, if Z were X, okay, so if Z and X were the same point, that would say that X is on both this line and this line, okay, and it's on this one here. So let's see, what would that say? That would say that it would intersect EF, so that would say that this line would intersect EF at point Y, but it also would be intersecting up here at point X. And remember, we can't have two distinct lines intersecting at more than one point. Okay, so one of the things that we said is that these are going to be distinct. These lines are distinct, and why are they distinct? Well, these can't be the same line because we've said point E is not on AB or CD, so it's not on AB. So they're not the same line because E is not on this point, on this line, and so that keeps it from degenerating to the to be the same line. Okay, and so that keeps X. Z cannot be X. Well, where else could Z be? It's got to be on these lines. Well, it's either over here on the C side of this line. So it's either got to be ZXD in that order, or XD or CXZ, either order. Well, I'm going to just choose one, and so we're going to let Z be actually over here, so that it goes ZXD. And if it's not that way, just relabel C and D. Okay, so without loss of generality, we can assume Z's over here. Now the drawing gets a little wacky because it's saying there's some point out here. Okay, somewhere out here. Wow, I drew a. Okay, wherever this is out here. It's supposed to be a Euclidean line segment there, I think. So the thing to notice, so this is a Euclidean line segment. But the problem is that you can't illustrate here. It's because these really are parallel. There is no point out here where these two lines meet, so I can't really illustrate it. So what we're illustrating is this line, red line segment, is actually part of this line EF down here. And the same thing in this picture. This points out here somewhere, but this red line segment is part of this line here. So that means that Y is between Z and F. Of course, it's not in my illustration. That's essentially going to be our contradiction, sort of. But we're assuming that that's happening. Okay, so the drawing's a little deceiving, but we do have a triangle right here, and here we actually do have the triangle. Okay, so let's go on from there. And so now, what do we have? We have Z, Y, F. Y is between Z and F. Y is between Z and F down here. Okay. And we also have a triangle X, Y, Z. Okay. Well, we got 3 points that are non-collinear and not an antipodal pair because we're in an unbounded metric. And so we actually do have a defined triangle. Okay. And what do we have with that triangle? Well, since this is a straight line here, and Z is on this line, okay, then this is an exterior angle of that triangle. FYX is an exterior angle. Now, for that to be an exterior angle, this red has to be down here on the line FE, but we're assuming that's true. Okay, so same thing up here. This is an exterior angle to this triangle. For that to be the case, this F to Y to Z has to be a straight line. Again, we're assuming that. So that's an exterior angle. But then we have a problem here because why? Well, when the metric's unbounded, we know that the measure of that exterior angle is greater than the measure of each of the remote interior angles. That's the exterior angle inequality theorem. And so that's where we reach a contradiction, is that the exterior angle says that this is greater, but what do we assume in our hypothesis is that these are congruent, so they have the same measure, and so that's a contradiction. Therefore, the only place we made our supposition was right back here, that they're not parallel, and so therefore the two lines must be parallel. So that's the Z property, the one direction of the Z property that's true in it's true in neutral geometry, and of course, by saying the metric is unbounded, then it's, we've as part of the hypothesis, it's true in unified geometry. So we have this proof, and we're done with that part. Now, here's the broader theorem here. We'll now say that same setup, okay, and the first part is that it's pretty easy. It's just saying that even though there are 8 angles formed here, we have at most 4 sizes, because these two that are the same color, the red ones here, the green ones here, the blue ones here, or the purple ones here, are vertical angles, and we know that vertical angles are congruent. So now we've gone from 8 angles down to up to 4 measures. So we could have at most 4 different measurements there, and that's what part A says. We just proved part B, the Z property. Now, I'm going to assign these to individual students for projects to prove part C, D, E, and F. And when you're going to prove these, whoever gets these as assignments, notice that you can use the Z property part B. So basically how you want to prove these is prove that when C is true, you can get the Z property and then get the conclusion you need. In the same way, go back to the Z property each time. Then part F, if we can show that if you have the Z property, then you get only 2 sizes of angles. So here we have 4 different sizes of angles, and in fact, these 4 sizes are all, you can clearly see that these here in a general transversal are not necessarily the 2 here, although there's some supplementary pairs here. and we have supplementary pairs here, okay, on this one, that they don't necessarily match up between these four and these four. But in the picture that we have over here, they in fact do. And so the red, let me make a hide show button for this and get rid of this now that we've eliminated this. Try that again. Okay. Okay, so there we have this. The red ones are all congruent and the green ones are all congruent, basically. So alternate interiors are congruent, corresponding ones are congruent, alternate exterior ones are congruent. And if they're on the same, if they're not congruent pair, then they're supplementary. Okay? And so that's what the last part of the theorem says. And so when you're proving this, whoever gets the job of doing the proof of the last part, you're going to want to show that if the z property is true, we get these, and then you can assume that in parts C, D, and E that somebody has already showed that if you have these other properties, then the z property is true too. And you can use that to prove your part F. Okay? So notice these start with some congruent angles, basically, and then show us that the lines must be parallel. So we're going to investigate the converse of that a little bit later on as well.